Tanuja is co-founder of DataGlen, which is a early round startup in the space of solar energy. Tanuja was earlier a technical staff member at IBM Research. She finished her master's from ISC. So it's a pleasure to have you. And she's also part of the summer workshop that we have here. So she'll be around for next couple of weeks.
Thanks, Pratik. Good morning, everyone. It's great to present some of the work that we are doing, and I think it's very relevant to Edge Analytics part that we are talking as part of the workshop. So as the name suggests, I'm going to talk about bits and joules. So some of the use cases in energy vertical, and what are the challenges, how the paradigm is shifting, and how the modern days technologies or digital technologies of IoT and AI are relevant for some of the problems that we are trying to solve in energy vertical. So as all of us would agree that energy is a fundamental necessity of modern society, and as we have the access to clean and cheap energy, we can do a lot in terms of the other sectors, including the healthcare and education and various other factors. So it's important to basically look at the problem of energy, which is a driving factor for various other industries and technologies in terms of the innovations. And energy vertical right now is going through a paradigm shift. And we call that paradigm shift as democratization. So on the left-hand side, you would see the democratization of media. So few years back, or let's say 20, 30 years back, the media was pretty centralized. So there was content which was created centralized way, and the content was basically disseminated in a distributed manner. So it's like Doordarshan or BBC who is creating the content, and the mass media is, as in mass population, is basically just absorbing the content. But now in last 10 years, there is, with the social media like Facebook and YouTube, everyone can create the content and everyone can consume that content as well. So it's completely changing from the centralized to decentralized manner. Very similar thing which is happening in the energy vertical right now, which is democratization of energy. So previously there was central generation which was happening at the form of the hydro or thermal energy. It was distribution and transmission was happening through central entities. Again, in India, most of the utilities are doing the transmission and distribution right now. And the consumers, who are basically the residential or industrial consumers, are just consuming the energy without participating in the entire model. But now we are shifting very similar to social media. The change is happening in the energy vertical as well. So there is distributed solar and batteries which is coming into picture. There are electric vehicles which are basically getting commercialized right now. So it's completely changing the way the energy was generated and consumed. So now the commercial or residential consumers are able to generate their own energy. Part of that they might be consuming, part of that they can basically inject back into the grid as well. So it's not a one-way flow, but now there is a two-way flow of energy which is happening. Obviously, the traditional power plants and traditional transmission distribution network is not designed to handle this two-way type of communication or two-way type of energy flow, and hence there are a lot of interesting socio-economical and technical challenges which are getting created because of this. So we would go through some of the issues in energy vertical and how the systems are, how the computer systems like IoT and AI can help solve some of those issues. So the first issue is of power shortage. So on the left-hand side, this is the power consumption, basically the power demand from New York over the year. So basically this axis shows over the year how there are variations in the power demand. This particular axis shows the during a particular day how the demand is varying. So during a day, again, there are one or two peaks depending upon the power consumption needs, and depending upon the season, whether it's the summer versus winter, there is a variability in the demand. So now if we look at these plots, these are again from the New York City. So there was the highest peak load demand year, which was 2006 versus the 1980s. If you see that there is no long tails in this kind of distribution. So these are basically hourly loads in terms of megawatt hours. And as we are moving to 2006 and again to 2018, we see very long tails of demand which are there. So the demand is increasing. There are short periods of high demand, And definitely to cater to these kind of demands, there is no point in adding the infrastructure just for catering to that peak demand load. So definitely there is some other methods or alternative methods are required to curtail to or address to these kind of demands which are coming on all the networks. The second problem is of energy scarcity. So in general, there is a problem of access to clean and cheap energy. So this is something which we have very much experienced in India, where there are regular power cuts, or there are places where there is no access to energy as of now. So this figure is from 2018, which shows that across the world, how much population is without electricity right now. And as we speak right now, there is still approximately 300 million people in India who do not have access to energy. And that's because of various reasons of the cost which is required for the transmission and distribution of the energy which is generated at the central level, as well as the other problem of the availability of energy itself. So current energy generation which is happening through thermal and coal power plants in India, which is not sufficient to increasing demand of energy at various places. The third issue that we will talk about is mainly the good part which is happening is there is a lot of renewable and alternate energy sources which are coming in picture right now in the form of solar, wind, as well as battery storage, etc. Good parts are they are quiet and local, so there are no transmission and distribution losses involved here. They are sustainable and scalable, so you can scale these plants as required. And most of these solar and solar especially is reaching grid parity, which means that the cost of generation of energy from solar, which is becoming almost same as cost of accessing the energy from the thermal or the existing conventional plants. But there are some disadvantages by using these kind of renewable energy resources. The first problem is generation variability. So this plot shows the generation across the year from one single wind turbine. So as we see that there is a huge variability across the year, as well as during one given day, there is a huge variability in the generation which is happening from single wind turbine. So when we are taking into account the large adoption of renewable energy resources, if we are not able to predict how much amount of energy that would be generated in next few hours, then we cannot do the unit commitment, and we cannot rely especially on these kind of sources. So it's very important that how reliably we can predict how much amount of energy that would be generated from these renewable energy resources, and it includes the accurate weather prediction, and on top of that accurate prediction of the energy from these sources. The second problem is if we take into account, let's say, solar, then the solar is available only during few hours of day. So it's available only from, let's say, 6 a.m. to 6 p.m. of the day. And again, there is a variability in amount of generation which is happening from a solar plant. So we cannot rely on this renewable energy resources completely. We need to have additional systems in place to back up the whenever these resources are not available. And that's where basically we are looking into the storage technologies and how storage and other technologies can be integrated with renewables so that we can reliably provide power supply through these renewable energy resources. So that's where now we are going to talk about the participatory grid. So now the consumer is not just the endpoint, consumer is not the dumb or static consumer, but consumer is participating in the entire process of energy generation and consumption in various manners. So the four main points that I'm going to talk about is first is how we can address the power shortage problem by reducing the peak demand. And the second is how we can address the energy scarcity. On one side, there is a energy scarcity, which means that amount of energy which is available that is not sufficient to cater to most of the energy resources. But on the other hand, we see a lot of energy wastage which happens in the residential, commercial and industrial places. So can we identify the energy wastage and curtail those energy wastage points? The third one is how we can basically maximize the distributed generation, or basically adoption of distributed energy resources with the additional resources like solar and other technologies. And the final one is looking at optimal utilization of resources, which means that basically including all the points of preventive maintenance and predictive analytics. So just going back very quickly to IoT technologies and why IoT and analytics is very suitable to serve some of these problems. So we are looking at basically the things which are equipments set up at most of these renewable or the conventional energy resources. Most of these are capable of communicating data over standard protocols. So we do not have to, in most of the cases, we do not have to add any new sensors as such. The existing batteries, inverters, wind turbines, or even the smart meters which are installed at the home premises, they are capable of sending the data and the context information as well. And there are some existing processes in place which need to be adopted to basically look into the new technologies. So I like to basically look at the IoT stack inspired from the similar to brain architecture. So as we look into the brain, there are different systems which are responsible for different types of actions which are performed in our body. So if we look at the reptilian brain, it's basically governing all the important or survival instincts of human body, including breathing, heart rate, and balance, which are like low latency response events which are required by the body. So those events are basically being handled very close to the sensor systems. The second type of brain is limbic system, which is looking at the feeling and memory formation. So looking at more data and generally forming the patterns or memories through that. And the last one is basically neocortex, which is doing the reasoning, forward planning, language, and other things. So this is basically looking at more holistically the data on from multiple sensors and making the decisions on top of that. So can we look at the IoT hierarchy of systems in similar way? So we have sensors and actuators at the level which are many times provided by the equipments. Then we have data loggers or edge devices which are sensing and collecting that data and capable of taking certain actions. So the actions which are required as a low latency response actions, or the decisions which are crucial to be taken in the very near real time, it's good to have those decisions in the system which are as close to edge as possible. Then there is there are certain decisions which require information from multiple resources. So let's say if we are looking at the load across the community and some decisions that need to be taken on top of that. Obviously, we would not be able to take those decisions at edge devices, but it might be in the fog or the local data center or the small computing which is at, let's say, community level where we can access that, and obviously in the cloud. So there was some initial work we did while I was at IBM on looking at hierarchical decision systems. So can we do the analytics in the hierarchical manner, where one node is doing the computation which is possible and essential by that particular node and passing on information to the next level of nodes. So depending upon the problem, can we decide where the analytics should reside for that particular problem, and can there be a connection between those nodes? So we have not completed this work after I left IBM Research, but we are interested in taking it up. So if there are any interest in the similar kind of systems, we'll be happy to collaborate on this. So obviously the neocortex is doing various types of analysis on image and time series data. So getting back to the participatory grid, I'll start with the load shifting problem, which is basically looking at peak power demand. So why reducing the peak is important? So as we see that it's the x-axis is the time of day and y-axis is the power production or the demand. So there are multiple peaks during a day, and the power is submitted as in the power is generated by various different types of load systems. So one is basically base load, which could be a hydro or thermal, so which is a constant load which we are getting throughout the day. On top of that, there is an intermediate load, which is again provided by some conventional energy resources. And then there are peak loads, which are typically provided by diesel generators, which have low response times, quickly can be started and run through. But if we look at the right side plot, it shows the amount of basically the price versus the power generation, and the price does not increase linearly. As we go to the peak demand, the price increases exponentially. So if we can reduce this particular demand from a very small tiny amount at least, it significantly helps in reducing the price in this particular band when it goes exponentially increasing. So there are historical approaches which have been taken into account previously to shift these loads. Some of these approaches have been daylight saving time or the Tokyo brownouts or CA rolling blackouts. Also in India, we see that there are these kind of load shading which happens like a few hours a day at different localities to cater to the demand. So some part of the community would be completely shut down during a particular point of time. So this is more like a top-down approach where the utility is deciding that I am not able to cater to the peak demand. So I would shut down part of the community and that would be basically a rolling load shedding that we see often during the summer times. There are a lot of other approaches which are being tried out in Western countries, including US and Europe, with variable degree of success, which are called demand response. So basically, if you look at the left-hand side, it shows the typical residential demand, and what part of the residential demand is the deferrable or time-shiftable routes. So if we are looking at electrical vehicle charging, that could possibly be a time-shiftable route. Or if we are looking at water heater or washing machine and dryers, those are time-shiftable loads because it's not like you need it immediately, but it can be done over, let's say, a period of 3 hours of time. So there is large proportion of loads in the residential, commercial and industrial loads, which are kind of time-shiftable. And can we take advantage of those loads to shift from peak time to off-peak time so that we can reduce the demand of and basically do the peak shaving during those times. So when we started looking into basically the problem of peak demand and demand response for India or the developing countries, the first challenge is in the way it's being tried out in US and Europe is utility collects the data from the smart meters or individual appliances. Let's say what washing machine is in demand response. Then there is a IoT device which is sitting on the washing machine. It's sending the data to the cloud, and utility sends the demand response signal either for the manual intervention or automatic dispatching the load to the some other times. So it requires basically complete infrastructure for communication, centralized optimization techniques where utility can send the signals to the consumers and the consumers would participate in demand response. There are few success stories in certain utilities in US who have successfully done the demand response process for shifting the load. But when we started looking at the same problem for, let's say, India and Africa, we do not even have the sufficient infrastructure for the network communication. So we cannot rely on the network communication to send the signal from the utility to individual equipment. Also, there are a lot of equipments which are already existing, so we cannot change those equipments, which means that there has to be something which is sitting outside of the appliance. So, but still taking into account the appliance's preferences. And the third thing that we wanted to look into is it has to be as cheap as possible. So it has to reside on a small device. And the third thing is the same kind of appliance should be applicable for a range of appliances. So it should not be that one type of appliance is only running for water heaters versus washing machines. So it should be able to handle multiple different types of time shiftable appliances. So taking these multiple things into account, we built something called NPlug. Again, this is a work which I did while I was at IBM Research. So what this NPlug does is, it's like a smart socket, or it's like our the power strip that we generally use. So it sits between the wall socket and the appliance. The appliance goes into the NPlug. And this NPlug is built using a 16-bit microcontroller with a very small 8 KB of RAM and 4 MB of flash memory. So what it does is it basically does local sensing and decision making. So it senses the grid conditions, especially of voltage and frequency, to identify whether there is a high load on the grid or not. It takes the preferences from the consumer. So let me take an example of water heater. So let's say most of the times our water heaters are, they can be kept, the water can be kept heated because there is an insulation available for 3 to 4 hours in the morning. So most of the times what happens is we all get up at 6 o'clock and start the water heaters. Water heater takes from 2 kilowatt to 4 kilowatt of energy. Multiple such appliances come in the activation, and we see the morning peak. So can we, instead of everyone starting and manually switching the appliance at 6 a.m., can we switch the appliance anytime between 3 to 6 a.m., because water can be anyway kept hot and ready for 3 hours. So the user can set the preference that I want the water to be ready at 6 a.m. and it can actually it needs to be run for 30 minutes, let's say, for water to get heated. So then we can actually shift this demand from 6 to 6:30 or whatever time the user gets up, and 6 to 7 a.m., let's say it's the peak demand time. We can actually do it anytime from 3 to 6 a.m. because that's the off-peak time. There is no much high load on the grid. The user can set the preferences that 30 minutes is what I want to run the appliance, and the 6 a.m. is the time by which I want the water to be ready. Obviously, there are override buttons, so some days, as in you don't want to set that schedule, so you can always override and say that I want to switch it on at whatever time I want. So without having any external infrastructure and just having the sensing of voltage and frequency inside the grid, inside the appliance itself, we wanted to see how we can identify the peak and off-peak demand times. So the first part is an autonomous operation or decision making of identifying when there is high demand on the grid. So this plot shows the time of day versus the voltage, and each color is a different day of the week. So this is the data which was collected from my house in Indiranagar. So in the morning you would see that or overnight the voltage is high because these are the off-peak times. The voltage is above 230, as in nominal voltage we are expected to have like 230 volts, but typically at night we will see it around 245 or 250 volts. Whereas in the evening peak times around 6 to 9, you would see significant drop, which is like 220 volts. And this was in Bangalore, where this local transformer was very close to my house. We did similar experiments at various different parts in India, and we see huge variability. So if we go at some of the rural places in Kerala, we have seen the voltage dropping up to 180 volts or 175 volts. So we cannot just fix a particular range, because the range varies across as you go from one location to other location. So we cannot just say that anything above 235 is the off-peak time and anything below 220, let's say, is the peak time, because depending upon the location, you have to adaptively identify that what is the peak and off-peak time range. So we collected the data. So we basically collect the data at every 30 seconds or 1 minute time interval, and put the compression on top of it, like piecewise aggregate approximation for aggregating the signals at every 5 minutes time interval. And then we look at basically doing the clustering of these particular time series into 3 clusters of peak, off-peak, and the median time. Then we look at the patterns. So let's say the algorithm looks at the last 10 days patterns to identify what are the peak and off-peak times. So based on that, it decides that okay, these are the it identifies first of all the thresholds, which is the lower threshold and upper threshold for voltage, and then identifies that based on last 10 days pattern that this is a time which is a peak time and this is a time which is a off-peak time when we need to take the control. This was, as in previously there were a lot of techniques which were looking into the frequency data to identify these gaps between the supply and demand. There was a lot of work on this, but no one has looked into the voltage signals and patterns, so that was one of the contributions. And doing these on these small microcontrollers in a streaming manner is what we did. The second thing is looking at frequency. So frequency would be, ideally it should be 50 hertz and close to, if we look at the data from US, we would not see this much of variability. It's pretty close to, let's say, 60 hertz over there. But here we see a huge variability from, let's say, 49.2 to 50.2. But still there are events when it goes beyond the normal threshold. So we identify what is the normal behavior for frequency and which are the times where there is an imbalance. So if the demand is higher than generation, then the frequency would drop. So we identify those events and again capture for shifting the load. So now we are able to identify the off-peak and peak times, and we know that when we should not be running the appliance. But let's say now there is no central control as such. Every device is going to make the decision independently. So we should not create a problem of just shifting the load from one time to another time by all of them starting and shifting. So let's say all of them sense there are 1,000 n plugs, and all of them sense that it's off peak time, and all of them shift to another time and create another peak demand. Yeah.
So what's the disadvantage or what's the issue if a device is running at a time when it's peak load and the voltage is low?
So basically you are adding to the peak demand. So if you are running the water heater, and since utility is not able to supply during that time, because there is a cap on how much energy utility can supply at any given point of time. So you would have experienced, let's say, morning and evening power cuts, right? So they typically do the power cuts during peak time because they are not able to cater to the demand at that time. So that's like a top down approach. They force everyone to shut it off. But what this one is trying to do is like a bottom up approach, that the device itself says that I need not run only during the peak time, so I can shift my demand. There are other loads, right? As in, let's say there are lights and air conditioner and other things which are not time shiftable. So we have to run those appliances during peak time. So giving chance to the appliances which definitely need to run during that time, and shifting the loads which are kind of voluntarily, rather than utility forcing, saying that entire community would go down from 6 to 7 a.m.
But are there any incentives for the consumer to do
Yeah. So basically, we then discussed with utilities on how they can include as part of the business model. So for industrial consumers, there is time of use pricing, right? So even in Karnataka, there is a time of use pricing where industries are charged higher rate if they are running it on peak time. So we discussed various business models if they can give a rebate if someone is running the load. So let's say if this particular device is able to send the audit log at the end of the month, which shows that it was not running during the peak time, then there could be discounts and rebates, as well as if there is a time of use pricing, there is a straight use case for the consumer to shift the load during from off peak time. Yeah.
So in your water heater example, you have to instrument the water heater to understand what kind of load pattern it generates. For example, washing machine you can't run for, water heater you can run for 10 minutes, shut it off if you realize the voltage is going down and bring it back up. But washer dryer you can't do that, right? Is that part of your model?
So that's part of the user preferences. So there are certain loads which are like a long running load. So if you take an example of EV charging, that would be running over 4 hours, and you can basically chop that 4 hours into, let's say, 6 hours with, you can say that my window size need to be 30 minutes. So you should not be switching too often. So if I give the chance for the appliance to run, it should run for at least minimum of 30 minutes. So that's part of the user preferences. User can say that, do I want to run it at one go, which is a case for, let's say, washing machine, that I want to run it at one go, versus if it's the inverters that we charge at home, or the electrical vehicles, or even the water heaters, where it can be chopped at, that entire usage can be chopped at multiple time windows.
Today I have to go and program this box on for the electronic device to perform. It's not as if the electronic device has some profile that it will export.
Yeah. So the way we had designed it, user has to provide the preferences. We wanted to keep minimal intelligence in the device, taking into account the small size of that. But that was a requirement from a few discussions that we had, that if the device is capable of providing the usage pattern, let's say, can we identify, let's say we can just collect the data of power consumption of an appliance, can we categorize what type of device it is? So can we categorize, classify basically the water heaters from washing machines, and then automatically put the preferences of what category of device it is. Yeah.
There's a different end plug for each device?
It's the same model, but if you are running it for multiple different appliances, you would be putting one for each.
And they talk to each other?
In this model, it was not, but then there was some conversation on, let's say if there are 10 n plugs within one industry, can they talk to each other and do some better, even better optimization in terms of distribution.
The basic nature is of is that typical of when the power generation system is constrained, or even say in the West where
So probably overproducing. Even there you can see.
Yeah. So we did these experiments on the data collected from, let's say, US houses as well. As I said, the variability, the range was small. So even in case of frequency and voltage, the range is very tight, but still you would see the pattern. So the pattern is available over the tight range over there.
I thought in Europe they said that drops based on 50 hertz signal.
Yeah.
So this is valid even in countries where they always insist on 60 hertz.
Yes. So you would see a small variability still. So the variability might be in, let's say, 10 raised to minus 2, but still the variability is available over there. And to control this, a lot of utilities put additional devices for doing voltage stabilization and frequency stabilization. So a lot of in India, while the utilities, or I think in few countries in Europe as well, the pricing of so in the real-time energy market, the amount of price that you get paid for providing energy at a particular point of time is called ABT, availability based tariff. That's dependent on the frequency at that time. So if the frequency is low and if you are supplying energy at that time, you get paid more versus if you are supplying in this particular region.
US and Europe, they do this demand side management, right? So, do they export all the data to the cloud and process it?
Yes. So again, there are. It's not widely available as of now. It was initially done as part of the pilots, and now as they are putting smart meters, the demand response is generally done if there is smart meter is available, because smart meter is giving you timestamp data already and being pushed to the cloud almost in real time. So that's where the analysis is happening in the cloud.
Since we're monitoring load, shouldn't we monitor the watt usage rather than the voltage?
So, so I'll go to the other problem where we do look at the power consumption of the appliance. But in this case, it was mainly for identifying how much, what is the condition of the grid, whether the grid is overloaded or not. So if you look at the power consumption part, you would just get to know that how your appliance is working, but you would not get to know that your transformer is overloaded right now, and you need to basically curtail your demand at this particular point of time. So basically, once the problem of identifying the grid condition was solved, then we wanted to look at how we can basically distribute that spread that demand over time. So we looked at various decentralized scheduling techniques, and we basically looked at computer networks, CSMA kind of protocols, which try to back off when there is a high demand on the network. So we call this algorithm as grid sense multiple access, similar to carrier sense multiple access. There are few differences in this one. So if we look at the CSMA or computer network algorithms, there is no deadline for completing the packet transfer. So you can basically attempt and send the packets, whereas in this problem there is a deadline. So if I'm saying that I want the water to be ready at 6 a.m., then 6 a.m. is my deadline, and I need to, no matter what, we want to give preference to the user's deadlines. So which means that the water has to be ready by the deadline which is given. So we had to basically do some modifications to CSMA kind of algorithms to suit to the deadline based algorithms. So the first thing that we did was contention window. So depending upon the available time slot, so let's say if I'm at 3 a.m. and I have 30-minute slots, so I have 3 hours, which means 6 slots which are available, or 5-minute slots, whatever number of slots which are available, the current time slot during that particular 3 to 6 a.m. window, and how much time I need to run that. So depending upon that, every device basically tries to identify the contention window, and as the time elapses, as you start going towards the deadline, your contention window size starts becoming smaller and smaller. So what the device does is, let's say if I have 7 as the contention window size, device chooses randomly to sense at any of these initial 7-minute slots and sense the grid and identifies whether it's the loaded or not. So by doing this, we are first of all distributing the amount of n-plugs which are sensing and making the decision at the same time. The second thing is the probabilistic connection. So depending upon the voltage levels, so let's say if the voltage is below peak load, then it says that you should not be joining because it's a peak time. If it's above the upper threshold, which means that it's a off-peak time and device can definitely join at any point of time. If it's in between, then basically it computes probabilistically that with how much probability that you should be joining the grid, whether you should be starting. So by doing these kind of probabilistic arrangements, not all n plugs would again join at the same time, but they distribute probabilistically and would not increase the load beyond a critical point. Yeah.
Given the user is plotting the preferences, right, wouldn't it be optimal to do a central control at each house level, which most queries and processes?
So we did some experiments on, let's say, if there are two controllers, two n-plug controllers in one house, obviously it would give, if they can communicate between each other, there would be better chance of optimization than this one. If you are able to do it centrally, that would be a complete optimal solution. So as we go up in the hierarchy or from the edge to fog to cloud, it might be giving you, because you have higher information available with you, you would be able to do better optimization. But taking into account the constraints of, we didn't want to add any communication infrastructure, not even the connection with Wi-Fi or the other points. So because of that, we decided that we would make the decisions locally and we would see how much difference it comes to. And if there are not many sensors, if there are not hundreds or thousands of sensors being controlled at one location, this one still gives the same performance as if it's 2, 10 or 100, it still gives the same performance. I couldn't hear.
For a household, this is still okay to have.
Yes,
as opposed to industry.
for even households and industries which have less than, let's say, 100 or 200 devices, this still works equally as if you had taken the centralized decision.
And will you be able to work on understanding the user preferences, obtaining it automatically as opposed to the user's
Yes.
making?
So that's another, as in I can point you to the other paper, where looking at users' load, we try to identify what are their preferences of running the devices and based on the context of how they would like to run the devices over weekends versus, let's say, weekdays and other things. So these are the results of, we tried it in simulation and some controlled experiments in real world. So basically here it's creating 2 peaks during a day. There are different types of n-plugs like water pumps and washing machines, water heaters and inverters, which have variable preferences in terms of their time window, how much they want to run, their starting times, their end durations and other things. So we are considering, let's say, close to I think 400 or 4,000 of such appliances. And even when they are taking these independent decisions in a decentralized manner, because now they can shift this particular peak spread 3 hours or 4 hours before the actual time duration, it's able to actually significantly spread the demand over time.
Is this simulation or is it actual measurement?
This was in simulation. So we did various simulation and then we tried it in the controlled experiments of 100 devices. So 100 devices we ran on multiple different appliances and users set their preferences as their need. So we didn't have control over how they set the preferences. So now moving from the load shifting to energy efficiency problem. So as there is one thing is there is high demand which utility is not able to cater to, but on the other side we see that there is a lot of wastage of electricity which happens. The wastage could be because of the aging appliances like aging refrigerators or the cooling systems. In US itself, 30 to 45% of HVAC system operate at below efficiency levels. So this could be again because of 2 reasons. One is either malfunctioning or aging of the appliance or inefficient use of appliance. So it could be that the air conditioner is running while the windows and doors are open, which means that it's not running at the optimal levels. To address to these problems, what we did was something similar where it's called as socket watch, which again sits between the appliance and the wall socket. And now it looks at, instead of looking at the grid, it looks at the power consumption of that particular appliance. So we collect data of active power, reactive power and various other parameters which can be sensed from outside of the appliance. And then we try to model the benchmark model for that particular appliance. So here it's an example of washing machine which goes through different modes depending upon the settings that you choose on the water heat the washing machine, and it has different signatures of active power, reactive power. So we identify these states of the appliance, whatever appliance is running in during the benchmark time. So this is the learning phase when we collect the data and build the benchmark model. So here it's basically showing that there are different states of power consumption of the appliance and how the states are transitioned from one state to another as a Markov model. So with the probabilities of going from one state to another state depending upon various factors. So there are two phases. One is the learning phase when we identify the modes depending upon the active power, reactive power consumption, the states depending upon the time spent in each of the mode. So sometimes the same power consumption, but if it's running for different time intervals means differently or it's a different state. Then we look at the periodicity between those modes. So for example, if we are taking example of refrigerator, the defrost heating might be running once every day. So that's the periodicity of that. Or if we see the cycling of compressor, it might be running at specific time intervals, which is the periodicity, and then the state transition. So how the device transitions from one state to another state. And in the once you have the benchmark model, in the monitoring phase, we do two things. One is the standby mode correction. So if we identify that the appliance is running on standby, then it's switched off. And if we identify that there is a change from the benchmark states, then we basically alert as a malfunction or inefficient use of the appliance. So every appliance, while it consumes the power, it consumes the power in two forms. So one is the, so basically in your watts, well, it's basically the breakage of your power consumption, which is termed as, it has a phase angle, and it basically gives you two parameters, that how much is the active power, reactive power. Depending upon if your load is inductive versus capacitive, the amount of active power, reactive power would change. So the combination of active power, reactive power would define in some sense what kind of operation is happening in your appliance.
So that's not it's built separately. I guess you build for the amplitude, but you're saying by looking at this extra information, you could get a better model. Is that
So basically, if you measure any appliance's power consumption, you get these two factors of active power, reactive power. So it's just sitting outside and measuring power consumption. That's all it's doing. So there is a lag between, as in its power factor between the active power and reactive power, which is a phase angle of those. So here are some of the examples of identifying the issues. So this particular one of the refrigerators, as in this is the benchmark model. When you see that there is typically there are states like compressor cycling, compressor going on and off, which if you look it into the clusters, it basically identifies different clusters which are states in terms of power consumption, and there is a periodicity, so how much amount it stays in the compressor on mode versus compressor off mode. This refrigerator, after building benchmark model, we identified it to be basically changing the states, and then we looked back and found out that there was a gasket leakage. So what's happening is, since there is a gasket leakage, it's not cooling sufficiently, so it's not able to take it's cooling, so it was not identified by the user because it seems to be working fine, but it was never going into the compressor off mode because thermostat is not able to activate the compressor off mode. So if you see here, it's always on and there are no cycles of on and off kind of a thing. And if we look into the clustering or the states, here was the compressor off state which was coming periodically, which was completely missing from the actual operational model. So just moving next to the distributed generation part. So basically these are called microgrids, the examples which I talked about earlier, because they are doing the generation and consumption at the same location. So they are called microgrids, and there are various forms of microgrids like offline, which are completely working independently, or there are backup, or online, which are typically the solar storage and the house, where you are getting grid power as well as you have your own system of the grid. And there has been historically We can say the consumption and generation happening at the same place, so there are historically different microgrids, but obviously those are not efficient. So the problem that we discussed earlier, previously the user was just doing consumption, so it was simple on and off of a switch. Whereas now when the consumer is called as prosumer, where there is a local generation and consumption, the complexity of the problem is increasing on the consumer side. So this is like a time of use pricing which is provided by the utility. So depending upon whether it's a summer or whether it's a weekday versus weekend, there are different prices for per unit prices. And you have the solar generation, which is like we don't have much control over it. The generation is happening depending upon your weather. You can just predict the generation, how much it can be there. And you have a battery. So the control that you have is how much battery that you can charge and discharge. And again, the problem at this small scale is being handled at multiple different stages as well. So there are something which is called as virtual power plants, where you have multiple different types of power generation equipment. It could be wind, solar, diesel generators or batteries. So how can you activate, so basically virtually they create a power plant, and let's say if you have the requirement that this virtual power plant need to be supplying a particular amount of demand during time, how can you choose the right set of generation at right time so that the overall cost of generation is minimized. So starting from the individual household level to the large scale generation, the same problem is being tackled at multiple different levels. And
Is this a superset of all the problems that you talked about? Or are there things that you've talked about before that you don't have?
So in earlier two problems, we were still running with the conventional sources but tackling to the power shortage and electricity wastage. Here it's mainly we are taking into account other non-conventional integration, and that's happening at multiple different levels. So you can choose any subset or of power generators which are available. Each of them would have different pricing for per unit generation, and they have different availability times and different constraints. So taking all these constraints into account, how can you fulfill your demand in real time while minimizing the total cost of generation? So that's happening at individual household, industry level or the utility level. And the interesting part here is you need to make the decisions of which generations to switch on or off in real time. So this requires very much computations which are as close to the generators as possible. So if you are, let's say, collecting data from wind turbines and solar together, obviously you need to collect both the data and make the decisions on the cloud. But let's say if you are doing these decisions for the house, then it's good to make the decision at individual house level rather than collecting data at the cloud and making the decision because of the latency and network issues.
So, in general, for solar energy or wind energy, what's the cost associated that you need to optimize over?
So basically it's called levelized cost of energy, which takes into account additional costs of maintenance and all other things over the time of whatever period, right? So now if let's say we are taking into account batteries levelized cost of energy, you need to take into account how much battery life is. So whatever capex that you are putting in, you would be expensing it over 5 years time. And depending upon how many charge and discharge cycles you make, the battery's life is going to go down. So that is another constraint on when you decide how much to charge and discharge the batteries, that how many charging discharging cycles that you are taking into account. And each of these resources have similar kind of constraints. So there are some times when wind turbine, if the wind is too low, it would still generate energy, but it would run very suboptimally during those times. So your levelized cost of energy during those times would be higher. So it might be better off to run some other generator rather than running it on low. So here basically the problem is of forecasting generation from each of these assets. So generally now even utilities in India have started forcing every plant which is more than 5 megawatt capacity, they need to provide one day in advance that how much generation would be happening from their plant at every 15 minutes time slot. And then there would be revisions during the day. Similarly, for small houses, if we are running it for the individual small house or a commercial entity, we need to know how much generation is expected from these sources in real time. A day in advance so that you can do the optimization, and if there are changes, you need to be able to adjust to those changes. The second is similar to the generation forecasting. You need to do the load forecasting. So how much demand is coming from your residential or commercial place, and how would you be able to cater to that demand? And next is the optimization problem to comply with the policy. So yeah.
Flexibly mix locally generated power with grid power.
Yes.
There's no constraints at all. I mean, the single plants can draw 40% from there and 60% from there.
So it depends upon how the wiring is done inside house, but that's something which is possible. So it depends upon, so because of cost constraints and something, generally some people do that let's say solar power is supplied to only few appliances and grid is supplied to all the houses, kind of a thing. But the combination and mix is possible depending upon the wiring that you do of your house. And again, depending upon 3-phase versus 1-phase loads and other things, there are few constraints.
So if I'm generating power and supplying to the grid, does my revenue depend on the time of day also?
Yes. So there are two types of tariffs. So there is one is the consumption tariff, where the consumer is charged depending upon how much amount of energy user is consuming at specific time of day. Then there is other type of tariff which is called feed-in tariff. So depending upon how much amount of energy you are injecting into the grid, sometimes it's constant throughout the day, sometimes there is a time of use as well. Yeah. Okay. So this is the other problem where depending upon the pricing and the policies which take into account the additional constraints of, let's say, levelized cost of charging, discharging batteries and batteries life, the optimization need to be done on the grid. So this is the problem which we are working on right now. So right now we do day-ahead forecasting and push the results to the box or edge. And then we do small optimization or simple optimization if there are any changes. So we are basically working on how we can do the revisions on the box itself, because if there is network disconnectivity or other issues, and how we can basically provide the optimization in more robust manner on the edge. So yeah, there are penalties associated if your generation is not correct beyond 15% for each of the 15 minutes point. So these are the policies in India right now, and we need to be able to cater to those. So another problem which is not on the edge but which we are trying right now is this is the Microsoft Research Building. So if we want to have larger adoption of renewable energy resources, we need to be able to identify, the user need to be able to identify how much is the potential of solar on my particular roof and how much amount of energy that can be generated. So basically this identifies the area of the roof and classification of the roof. So depending upon whether it's a south-north roof or it's the east-west roof or it's a flat roof, the capacity of solar that you can put on it and its overall potential would vary. So we are doing some work on the image optimization on there, and there is already some open source work on that called Open Solar Map if someone is interested. That was mainly for the French datasets. We are looking at Indian datasets for this. And finally, the efficient operations. So this is mainly about the predictive maintenance and root cause. So since we collect data from various appliances in solar, there are different types of failures which are possible across various sensors, including weather sensors, inverters, MPPTs, and other things. So we try to identify predictively and reactively those faults and alert the users. This is the stack of data collected from the IoT platform right now, and this is how the real-time portfolio view looks like. So there is something that we are doing like an online-offline model where the central user wants to look at the entire data. So if I'm the independent power producer who has 25 plants across India, I would want to see in real time that how it's performing over my entire set of plants. But many a times these large plants are at remote locations. So there are always problems of network connectivity and other things. So if the entire model is sitting only on the cloud, the site engineers who are sitting at the ground, they are not able to access the system as well. So we have something like an offline sync model where it's a subset of functionalities available on the fog at the plant itself, and opportunistically it syncs with the cloud data centers. And then identifying various underperforming assets. So we have shared some data with Naga and team as well. So we would like to explore some of the techniques that they have used here. So this is the cleaning schedules. So cleaning is one of the important issues in solar, which drives the inefficiencies. So without adding any additional sensors, just at looking at the power consumption threads, we are able to identify when is the cleaning required and how much is the soiling losses. Again, this one we were doing on the cloud right now, and we are trying to push it in the edge as part of the workshop experiment that we are doing. And the last one is combining time series and image data. So one is we are getting this time series data of power consumption and other things from individual equipments, but we are also trying to get some data from either thermographic imaging or the normal cameras. So how we can combine these two to identify the right fault and decide what type of dust it is or what type of soiling it is and activate the auto cleaning mechanism appropriately. So yeah, there are a lot of interesting other startups and other corporates which are working on energy problems using AI and IoT technologies across the world. We'll be happy if there are any problems which are of your interest, and we'll be happy to collaborate with you. Thank you.